Ever wondered why relays, those seemingly simple electrical switches, aren't the go-to solution for every circuit? They're incredibly useful, sure, but like anything, they have their downsides. And if you're working with electronics, understanding these limitations is crucial. So, what are the disadvantages of a relay? That's exactly what we're diving into today. Relays are electromechanical devices. Think of them as tiny gatekeepers for electricity. A small control current energizes a coil, which then physically moves a switch to control a larger current. This makes them perfect for things like switching high-power devices with a low-power signal or isolating sensitive circuits. But this mechanical nature, which is their strength, is also the source of many of their weaknesses. First and foremost, relays are slow. Compared to semiconductor switches like transistors, relays are downright sluggish. That mechanical movement takes time. We're talking milliseconds, which might not seem like much, but in high-speed digital circuits, those milliseconds can be the difference between a system working flawlessly and crashing spectacularly. Imagine trying to use a relay to switch data in a modern computer. It would be laughably slow. This speed limitation makes them unsuitable for applications requiring rapid switching. Then there's the issue of contact bounce. When the relay's contacts close, they don't just make a clean, single connection. They tend to bounce a little, making and breaking the circuit several times before finally settling. This bounce can create spurious signals and glitches, especially in sensitive electronic systems. You can sometimes mitigate this with specialized debouncing circuits, but that adds complexity and cost. Another significant disadvantage is wear and tear. Relays are mechanical devices, and all mechanical devices are subject to wear. Every time the relay switches, those contacts rub against each other, gradually wearing down. Over time, this wear can lead to contact degradation, causing increased resistance, intermittent connections, or even complete failure. This means relays have a finite lifespan, and in applications requiring frequent switching, they'll need periodic replacement. This adds maintenance overhead and potential downtime. And let's not forget about size and weight. While small relays exist, they're generally bulkier and heavier than their semiconductor counterparts. In applications where space and weight are at a premium, like portable electronics or aerospace systems, relays can be a liability. A circuit built with transistors can be significantly smaller and lighter than one using relays to achieve the same functionality. Relays are also susceptible to environmental factors. Dust, moisture, and extreme temperatures can all negatively impact their performance. Dust can accumulate on the contacts, interfering with the electrical connection. Moisture can cause corrosion, leading to increased resistance and eventual failure. Extreme temperatures can affect the mechanical properties of the relay's components, causing them to malfunction. This means that in harsh environments, relays need to be carefully protected or specially designed for those conditions, adding to the cost. Another issue is power consumption. While the control current for a relay is relatively small, it's still a continuous draw. The coil needs to be energized to keep the relay in its switched state. In battery-powered devices or energy-sensitive applications, this continuous power draw can be a significant disadvantage. Transistors, on the other hand, often require very little current to maintain their state. Then there's the problem of noise. Relays, being mechanical devices, make noise when they switch. That clicking sound might be acceptable in some applications, but in others, like audio equipment or quiet environments, it can be undesirable. Solid-state relays, which use semiconductors instead of mechanical contacts, are silent in operation and are often used to avoid this noise issue. And let's not forget about complexity. While a single relay is relatively simple, complex logic circuits often require multiple relays. This can quickly lead to a bulky and complicated circuit, making troubleshooting and maintenance more difficult. Implementing the same logic with transistors would result in a much more compact and manageable circuit. Another disadvantage often overlooked is switching speed limitations. While we talked about the general slowness of relays, this also translates to a limit on how quickly they can switch. They can't keep up with the rapid on-off cycles required in high-frequency circuits or pulse-width modulation applications. This makes them unsuitable for many modern electronic systems. Finally, relays are susceptible to vibration and shock. Because they have moving parts, relays can be affected by mechanical vibrations or shocks. These can cause the contacts to open or close unintentionally, leading to malfunctions or intermittent operation. In applications where vibration or shock is a concern, relays need to be carefully mounted and protected, adding to the design considerations. So, while relays are incredibly useful for certain applications, particularly where high power needs to be switched with a low power signal or where isolation is critical, they're not a universal solution. Their slowness, contact bounce, wear and tear, size, weight, environmental sensitivity, power consumption, noise, complexity, and susceptibility to vibration and shock all contribute to their disadvantages. Understanding these limitations is crucial for any electronics designer or engineer. Choosing the right switching device, whether it's a relay, a transistor, or something else, depends entirely on the specific requirements of the application. With that said, thanks for watching, and until next time.